Hey guys, I couldn't make it in person to this session, so I'm gonna record a video of myself solving one of my favorite problems using work um, and energy, right? So the problem is basically you have these two masses. Let's see, we're gonna name them, or they're already named A and B, and after B has moved down delta amount. We're to find the velocities of both of these boxes. Um, for the sake of this problem, we're going to assume that the motion of A is upwards and the motion of B is downwards. Um, the first thing we're going to do is we're going to find the constraint equation, right? Whenever you guys are working with pulleys, it is important to find the constraint equations. We're going to use the tilted coordinate system for A and the straight vertical down coordinate system for B, right? Um, and then we're going to try to describe the lengths of the pulleys, right? So this length down here is YB, and this length to box A is YA, right? So with that equation, we need one more thing, right? So this distance, let's call the distance K. Um, And now to describe the length of the pulley, we can use the variables that we have set, right? Starting with A, we can see that it loops right here once, so that's YA. Um, this right here is YA minus K, and then this right here is YA minus K also. Um, so our equation is going to be YA plus 2YA minus K. And then for B, we can just see it loops to B twice. So plus 2YB, right? Um, an important side note, this pulley setup right here, if you set up the free body diagram for the massless pulley, you would get that a pulley setup such as, let's see, this is identical to a pulley setup such as this. So the math for it is the exact same. And you can verify by making a free body diagram for this pulley right here. Um, yeah. So for this problem, I'm just treating this setup as if for like the pulley was attached to the box. Right. So this is our constraint equation. Mm, Let's take the derivative of this equation respect to time, right? So dl dt. The length of the pulley is not changing, so it's equal to 0. We get velocity of A, right? Plus expanding that, right? Or let's try the expanded version so you can see. Derivative of the position of A respect to time plus 2 times the derivative position of YA respect to time minus 2 derivative of the constant K respect to time plus 2 dyb or dt. We got the constant does not change respect to time, so that goes to 0, right? Uh, grouping the like terms together, we get 3 dya dt plus 2 dyb over dt, right? And now the change in the position of A over uh, respect to time is just the velocity. So we just get 3 velocity of A plus 2 velocity of B is equal to 0. And then we can also say similarly, if we take the derivative one more time, right, we would get 0 is equal to take 3A plus 2AB, right? So this is our constraint equation, right? And then now if we apply, let's see, the work and energy equation, you get delta E system is equal to work external. Now, there's two different ways to solve this problem, right? What we can do is we can focus it on just one of the boxes, and we can consider the force by the pulleys or the tension force as an external force, right? Um, or we can include massive A and massive B, basically boxes of A and B, into our system. And then there would be no external forces because everything's internal. So we're going to do it both ways. So for part A, we're going to consider A and B as the system, right? In that case, right? So if we have delta E of A and B is equal to work external on A and B, which goes to zero because there is no external work. This problem does not mention friction at all. So you can ignore friction, right? Is equal to zero. With that, you get energy initial of A plus energy initial of B is equal to energy initial or final of A plus energy final of B, right? Um, there is no spring associated with it. Um, so the only energies, mechanical energies we have for boxes A and B is kinetic energy, right? Um, now we can also see right here, right? So let's actually, before we even get there, let's write down. So kinetic energy initial plus potential energy initial for A plus kinetic energy initial plus potential energy initial um, for B is equal to kinetic energy initial plus potential energy initial, excuse me, final of A plus kinetic energy final plus potential energy final for B. Um, Now we have some cancellations to make, right? First thing we're told that is that the system is starting from rest, right? So that means kinetic energy of A and kinetic energy of B at the initial state is going to be zero. So we can cancel those out, right? Now the potential energies, they're dependent on our coordinate system, right? So for both boxes, you can actually have two different coordinate systems for both of these boxes. Um, because it's the change in the height of both of these boxes that's what's important. But for the sake of this problem and to show you guys that mathematically they're the same, I'm going to choose my coordinate system at, let's say, we're going to choose it at the initial position, right? A box B, right? So my Y and X are here. And we need some sort of reference position from here to the center of gravity of the box or the bottom of the box, top of the box. It doesn't matter. You just need a reference um, side of the box, right? Uh, these are all at this point, point-like objects. So you just need a point on the box, right? So we're going to call this distance right here K. And what's going to happen mathematically is it's going to cancel out. And you guys will see that, right? Um, so if we set uh, the initial, if you set the coordinate at the initial state of B, right? Then what can happen is that uh, potential energy initial of B is going to go to zero. Now we can expand these equations out a little bit more. So what we get is mg height of A is equal to 1/2 mv A squared, right? Plus mg h of A plus 1/2 mv B squared plus mg h of B. Okay? Um, Now, if we said, let's see, let's focus in on A, or let's focus in on B first, right? Um, if this right here, let's draw the hill, actually, right? This is an angle theta. This is your box A. This is A, this is A, this is the final position, this is the initial position. Um, and once again, this is the initial position, this is the final position, right? And if we set our coordinate system right here, and if it went down by a delta amount, our h of b final, or our height of b final, would be negative delta. Um, for A, it gets a little bit more complicated, and what we're going to have to do is we're going to have to look at the constraint equation, right? Which, going back, our constraint equation for the pulley is the length of the pulley is equal to y of A plus 2y of A minus k plus 3y of B, right? Excuse me, 2y of B. And we derived it earlier. 2y of B, yep. Um, Now we're going to set initial and final states of the constraint equation, right? So what we're going to do is length of initial is going to be y of A initial plus 2y of A initial minus 2k of initial. And what you're going to realize is the k's are going to cancel out, but we can keep doing it and you can see it for yourself. Initial. Similarly, for the final state, we're just going to label it YA final plus 2YA final minus 2K final, 2YB final, right? And what we're going to do now is subtract LF, length final of the rope, minus length initial of the rope pulley, right? That's delta L. And we know that the length does not change, right? The actual number of the length, right? If the length was originally 3 meters, it stays at 3 meters. So what we're going to get is the change in length is going to be equal to 0, right? And that is equal to YAF, I'm just plugging it in, the equation, right? Minus YA initial plus 2 YAF final, YA initial plus K final minus K initial. Um, Plus 3YB, or excuse me, 2YB final minus YB initial. And what we find out is that this right here is going to be equal to 0, right? And that's because the constants do not change over time either, right? So if this constant, let's say, is equal to like 1 meter, right? So then the constant in the final is going to be equal to 1 meter, and the constant in the initial is going to be equal to 1. And 1 minus 1 is going to go to 0, right? So, that does not matter. And then simplifying the equation, what we actually get then is 0 is equal to 3 delta y a plus 2 delta y b, right? But we're given delta y b. Delta y b is just delta amount, right? This right here is delta delta y b, yeah, which 0 then is equal to 3 delta y a plus 2 delta b, right? Solving for delta y of a, we get delta y of a is equal to negative 2/3 delta b, right? And why this is important is because we want to find the rise of uh, the box A, right? So basically, if this moves a delta amount, we get that this right here, box A, moves, according to the equation, 2/3 delta B, right? Now, doing a little bit of trig, right? We can find out what the vertical rise is, right? So if this is 2/3 delta B, right? And if this is theta, and this is delta H A, right? Rise in the box of A, we're gonna get that 2/3 delta B sine theta is equal to delta H A. Okay? And the way we can describe the initial and final positions, right? So delta H or H A initial would be distance K. Another constant that we just chose, right? Or actually, you know what? We can choose another constant. I feel like this might be, let's choose a constant C. We can update that right here. So then the final position of A would be C plus delta H of A, which we found that to be C plus 2/3 delta B sine theta. Okay, now going back to our energy equation, we pretty much have everything we need to plug in, right? Um, so this is a little bit messy. We're gonna clear it up and we're gonna write so HB final is equal to negative delta, HA initial, excuse me, is equal to C, HA final is equal to C plus 2/3 delta B sine theta. And then we're also given the constraint equation that 0 is equal to, let's see, we derived it earlier, 3VA. So 3 times the velocity of A plus the velocity of B, or 2 times the velocity of B. That tells us that velocity of B is equal to negative 3/2 the velocity of A. So with this, we have everything we need to plug in our work equation. And just for the sake of clarity, I'm going to write it out again for you guys. It's this, or you know what? I can copy and paste it. So now we just have to plug in everything. We know that HA, um, this side is, remember, initial, right? This right here is the um, initial side. And this right here is the final. So HA initial is going to be just constant, some constant. So HA initial, HA is just some constant is equal to 1/2 MV A squared plus MG. Seeing a problem right here. No, excuse me, guys. I forgot to write down the variables. All right. So if this is of A, this needs to be MA, right? MAG plus 1/2 MVB plus, hello, hello. Okay, sorry guys, my mic turned off. Okay. We have this equation. So it's important to note that the energies are the mass. So like if we're analyzing the potential energy of B, right? The mass also has to be of B. Um, Similarly for A and the kinetic energy of B. So I'm just putting in the correct values right here. Let me see. Yep. So this is mass of A. This is of A. MgH. A. So MA. GHA. We know that HA final is equal to constant plus 2/3 delta B sine theta plus MV plus 1/2 MB VB squared. Right? So we know VB squared is negative 3/2 BA squared. Right? According to this equation right here. Finally, MBG. Now H of B final, we found out is equal to negative delta. Negative delta, right? So now we can do a couple cancellations. First, if we see right here, right, and if we're looking at the potential energies of the masses A, right, we're going to realize that this right here is going to subtract into right here. Right? So we can actually just cancel out C right here. Right? If you distribute this, you'll realize mathematically it will cancel out with this term right here. And what we can do with mass of B times gravity, right? Potential energy of B in the final state is, because there's a negative sign, we can bring it over for simplicity. So MBG delta is equal to 1/2 MA VA squared plus MAG times 2/3 SB, or delta B sine theta plus 1/2 MB negative 3/2 VA squared. Right. Remember, we moved this term over, right? And we are ready to plug in numbers. So at this point, you can either solve for velocity of A symbolically, like Professor Ellie does, and then plug in the numbers, or I was taught to use a numeric calculator uh, when it gets complicated like this. I can show you guys how to use it, but for now, I'm gonna use it. The numbers we were given is mass of B is 33. Let's see, I'll write it down here. Mass of B is 33 kilograms. Mass of A is 45 kilograms. Kilograms. Delta is equal to 1.2 meters, and theta is equal to 12 degrees, right? Plugging that into this equation above, we get 33 times 9.81 times 1.2 is equal to 1/2 mass of A, 45, velocity of A. That's the unknown we're solving for. Mass of A times 9.81 times 2/3 delta, which is 1.2, sine theta, which is sine 12 degrees, plus 1/2 MB, which is 33 kilogram, times negative 3/2. The negative isn't gonna matter since it gets canceled anyways, but we can put it right. Oops. Okay, so now the only unknown in this equation is velocity of A, which we can solve for using the quadratic formula. Um, or I'm looking at it, we won't even need the quadratic formula. We can just isolate velocity of A. Um, but I'm going to put it into my calculator and let my calculator do it for me. Um, so times x squared plus 45 times 81 times 2/3 sine 12 plus 0.5 times 33 times 3/2 x. Well, this gets squared. Right, yep. And we get that velocity of A is equal to 2.29 meters per second. Um, Downwards, right? Or let's see, A is, oh, up the hill, excuse me. So you get the direction from the initial assumption, right? That it's up the hill. Um, and then we also know that velocity B is equal to, you see a negative sign right here? So the negative sign is reference to the coordinate system for uh, A and B were set up in. Right now, since we know that B is going to go down anyways, we can ignore the coordinate sign or like the negative sign, and we can just do 3/2 BA, which then would be equal to 1.5 times 2.29, which is 4.34, or excuse me, 3.435 meters per second, and this is going downwards, right? Yep. So that is our answer. Now, this problem can be done another way, and I'm going to do the other way. So now, another way we can do this problem is we can just look at either A or B and consider the tensions acting on those masses as external forces. So let's do that. So mm, taking, we're just going to take B as our system, taking B as system, we get delta E uh, of B is equal to work external on B. So we get energy initial plus work external B is equal to energy final of B. Now, the only external work acting on B are the two tensions, right? And we can see that by the free body diagram. So let's set up the free body diagram, right? So this is our point, and I'm gonna label my axes such as this. This is my X, this is my Y. Um, this right here is my box, right? Upwards, we have 2T acting on it. We have the force of gravity, and those are the only forces acting on it. We know that the system's being let go from start, so it obviously has to accelerate, right? So force of first net in the y direction, we get 2T minus force of gravity, which is just mass of the object, B, times gravity, is equal to mass of B times acceleration of B. Mm, So that's one of the equations we need to try to solve for the external force T, right? Um, let's go back to the energy equation up here, right? And let's elaborate on that, right? So the initial energies are the kinetic energy, which we know is not present, and gravitational potential energy. Right? And we set our coordinate system like the previous problem, right? We're going to do the exact same thing, and we're going to set the coordinate or the reference coordinates at the initial state. I'm letting zoom load. At the initial state before it's being let go, right? So then if we do that, right, the height would be zero. So our potential energy initial would be zero, right? Um, so that means that energy in the initial state, because there's no kinetic or potential, can cancel out. There's only work external. Um, yep. So what we get, right, is work external on B, which is gonna be is which is gonna be equal to energy final, which is 1/2 mvb squared plus mghb final, right? Um, Similar to previously, HB final is gonna be negative delta, right? And work external is gonna be, if you remember, work is defined as some force, if it is constant, dot a distance. Now that's dot product, right? So force delta S. So if we're taking just the magnitude of work, it's going to be the magnitude of the force um, times the distance it's traveled. Mm. And the angle between them. So if we have a force, which is 2t acting on it upwards, but we know it travels downwards, right? We're going to get the angle between them to be 180 degrees, right? So we're actually going to get that the work is negative. Basically, energy is being taken out. Um, excuse me, the energy is being taken out of the system, which is mass B, which makes perfect sense, right? You need some energy to move box A. So the weight of B is contributing to moving the box of A, right? That makes perfect sense. So we're gonna get right here, right? If we do it right, we're gonna get 2t, the work acting on the system, times the distance that it travels. We know it travels a delta amount, right? Times cosine 180, which is just adds basically a negative for us, right? Cosine 180 is negative 1. So we know the work acting on it now. So negative 2t delta, I'm just plugging into the equation above, is equal to 1/2 mvb squared plus mg negative delta. We talked about the negative delta earlier. Um, and then let's just do some math on it. I'm just rearranging this. Very important to consider mass B. So all over mass of B. This is BG um, times the 1/2 power is equal to VB. Right? So this is all we need to solve for velocity of B. Um, if you realize we know delta, we know the mass of B, we know G, we know the mass of B once again. All we do not know is the tension force that's acting on it. So we need to find tension. We set up this free body diagram earlier, and we have one of the equations to solve for tension. But the unknowns that we're gonna get is A, acceleration of B, and then the tension force. Those are our three unknowns of the system. So if you have three unknowns, we need three equations to solve the system. We already have two equations. We found 2t minus mb times g times mb ab. That's one equation. We have a second constraint equation that We found earlier as we were starting the problem, right? Mm, which is, let me see, where is the problem or equation? Right here. Just gonna copy and paste this. So we need three equations to solve for the last unknown. So the third equation, we can find it out from the free body diagram of A, right? This is some theta. We're looking at the A on the hill, right? Um, there is a normal force acting on it. There is some weight force acting on it. Weight force, or the force of gravity, or mass times um, gravity. There is no friction in this system, and our axes are x in that direction and y in that direction. So if we take the net forces in the x direction, we're gonna get, um, oh, I'm so sorry, I forgot the tension forces in the x direction. Let's do, it's being hit with three tension forces because the pulley is wrapping around it three times, right? The pulley always, the rope or the tension force is always away from the object, right? So it's 3t. Okay, so we get 3t in the positive x direction. Once again, this is our x, this is our y. Now the normal force is fully in the y direction. We don't have to consider that. The x direction, weight of A is acting against, or it's in the opposite direction of our x direction. So it's minus MAG sine theta. You can do the trick for yourself, right? Is equal to some mass times acceleration. And this right here is the third equation we need to solve for tension. Right? We have, well, first unknown is tension. Our second unknown is acceleration of B. And our third unknown is acceleration of A. We have three unknowns, three equations. That means the system is solvable. And let's solve for it actually. Right? Mm, Let's look at equation number two. So rearranging equation number two, we get the acceleration of B is equal to negative 3/2 the acceleration of A. Now, if you look at equation number one, we can plug in equation number two into it. So equation two in equation one, we get 2 times tension minus mass times gravity is equal to mass times negative 3/2 A of A, right? We just plugged it into equation number one right here, into acceleration of B. And looking at equation number three, we get 3t minus ma g sine theta is equal to ma acceleration of A. So right here, between these three equations now, we have two unknowns and two equations, so it's solvable. I'm going to use a method, as should be taught in an algebra course, and we're just going to multiply this by -3, and we're going to add the two equations together, right? Actually, to do that, I'll have to also have to multiply this by negative or by +2. So scaling up the equation by -3, we get -6t plus mb plus 3 mass of b times gravity is equal to Now the negatives and the negatives are gonna go away. The 3 and the 3 are gonna multiply. It's gonna be 9 halves mass of B times acceleration of A. On the bottom side, we're gonna get 6t minus 2 mass of A times g sine theta is equal to 2 times mass of A times acceleration of A. Right. Now, we can just add these two equations algebraically. Negative 6t plus t is going to be equal to 0. 3mb minus 2g, we can do the math for it, so we're going to get plus 3mbg minus 2mag. Now, this is a technique that should have been taught to you guys in college algebra. Maybe in like simpler, maybe with simpler coefficients, but it should have been presented to you guys. Plus 2ma a of a. Right? Factoring out the acceleration of a, we're gonna get 3mb g minus 2ma g sine theta all over, let's see, 9 half mb plus 2ma. So that's our acceleration of a. Now we're just going to find that out. We're going to plug in numbers and find it out. 3, the numbers, mass of B was given as 33. So 33 times 9.81 minus 245 times 9.81 times sine 12 degrees all over 9 half 33. So while I'm doing this, you guys can already see how much more work this problem is compared to the other way of solving it. Just to contrast the two methods, mass of A is 45. And the numeric answer is, let's see, times 3 times 9.81 minus 2 times 45. I'm just plugging this into my calculator, guys. We're going to get acceleration is 3.302 meters per second squared. Acceleration, the direction we can infer, right? We know it's going up the hill, so the direction would be up the hill, 12 degrees, right? Now, since we found out the acceleration, um, we can simply just plug it into this equation, and we can find the tension force, right? So we can say A in equation 3, right? We're gonna get this. So 3, so tension is equal to 3 times, how do I want to do this? It's going to divide. Mass of A divided by 3, g sine theta plus acceleration of A. Tension, we know the mass of A once again is going to be 45 kilograms. So 45 divided by 3 times 9.81 sine 12 plus 3.302. Tension is going to be equal to, just plugging it in to my calculator, 1.81 sine 12 degrees plus 3.302, about 80.125 newtons, right? And now we can simply just plug it into the formula we derived earlier to find the velocity of B, right? So going back, we're gonna plug everything we know into here now, right? So delta is equal to 1.2. So 2 times delta times the mass of B. Mass of B is equal to 33 kilograms times 9.81 minus 2 tension, which we just found right now, 80.125. Now, the tension also, I did not add direction for tension because if you're talking about B or if you're talking about A, the direction of tension changes, but the value, the magnitude of it stays the exact same. So it's a little bit harder to put a direction on the tension force, right? Um, like the tension forces are the same, but if you were to say that the tension of A would be, let's see, since A is going up the hill, the tension force, right, if we were to add a vector, it would be going up the hill at 12 degrees, right? So it'd be like this. And then the tension of B would be 80.125 newtons. Would be going straight up, right? Yep. So the magnitude stays the same, direction changes. That makes perfect sense, what you guys learned in class. Now dividing all of this, right? Just by, this is really annoying. 1/2 mass of B again, which is 33. And taking the entire thing's square root, get VB. Now plugging in the numbers, I'm getting, let's see, 2 times 1.2 times 33 times 9.81 minus 2 times 80.125 times 133 and the square root, taking the square root of this, we get velocity of B is equal to 3.448 meters over seconds, right? You can infer the direction to be downwards, and that is very similar um, to the answer we found right here. I mean, the reason, let's see, our answer that we found is 4. We can attribute the difference in the numbers due to just some rounding errors, right? So, and you could solve for velocity of A the exact same way that you did, right? Before using this equation. Let's see. So we can solve for it real quick. We get that the velocity of A is equal to, just looking at the magnitudes, because the directions we can infer, and I've already talked about this before, 2/3 via B, which is equal to 2/3, for 3.448. So velocity of A is equal to 2.275 meters per second up the hill, right? As we previously said. So, right, like this, right? And the vector sign would go right here. Comparing it to our old answer, we got, if you were to round it, we would get 2.28. Once again, the rounding error can be attributed to just or the difference in the answer can be attributed to the rounding errors. Okay. Um, but this was the 2 different methods to solve this problem. There's a third way, which we took B as a system. We could have took A as a system. You guys can try that on your own. The the gravitational potential height difference, just a little bit more. Um, you would calculate it like we did in part A. But guys, I hope this helped. This was the two ways to be able to solve this problem. Any questions you guys have, you guys can email me. All right. Thank you so much.